Okay, so today we're going to go over something that relates to the quadratic formula, in that a lot of the answers that we can get, if they don't factor fully, end up being square roots. And we have to know the properties of square roots in order to be able to properly simplify those, and then as well as introduce some other operations and processes a little bit later on having to do with the fractional exponents. So let's talk a bit about radical number operations. Radical, really, and a square root sign are kind of the same thing, except, of course, not all square roots are square roots. Sometimes there are third roots and things like that. So let's talk a little bit about the anatomy of it first. So a radical is another word for a root. Not a square root, but a root, okay? We can have many different types of roots. The types of roots are called the index of the root. So for a square root, whenever I write this, it's assumed that it's a square root, and so we leave out the 2. Kind of like when I write this, it's assumed that it's x to the power of 1. Okay, you leave it out. But if it's anything other than a square root, then you put the type of root that it is, and that's the index. So if it's a cube root, then that's what number multiplied by itself 3 times gives you the number underneath the square root. The number underneath the square root is called the radicand, okay, or radicand. Okay, just like anything else, these radicals can have coefficients to them, just like x or y or ab can have a coefficient of 5 or 4 or negative 3. So can radicals. Okay, so radicals we can have multiple numbers of these. What they are they're a type of number that's called an irrational number. Okay, and an irrational number is a number that can't be written as a fraction using whole numbers on the numerator and denominator. And as a result, we write them as a square root. So, for example, the square root of 7. And when you take the square root of that, it just keeps on going on forever and ever and ever and ever and ever. Now, there's some numbers where you take the square root of them, it will give you a nice round, perfect answer, like the square root of 4, or the square root of 9, or the square root of 25. And we call those perfect squares, because when we take the square root of them, then the result is a single integer value. But most, if not all, of those numbers that are around those perfect squares, or perfect cubes, or perfect quarts, or whatever it may be, tend to be what we call radical numbers or irrational numbers. Okay? So, there are many different types of roots: fourth root, third root, cube root, second root. That's the index. The radical sign acts as a bracket. That's another key feature in there. Anything that's underneath this sort of square root, as long as it extends, and sometimes people put a little tick mark at the end of it. I tend to do that a lot when I write my operations. That suggests that everything in there is in a bracket. Okay, in that it all is together. It can't sort of just be distributed out and things like that. Okay, so radicals are a bit like fractions that can be written in lowest terms. So that's another feature that we'll be learning about today, as well as some properties. Okay, so let's look at some radical number operations. Okay, now radical numbers are very much like variables in that if you take a radical number, if they are exactly the same underneath the square root sign, if the radicand is exactly the same, then you can add them or subtract them together by their coefficients. Okay, so if you look at this example here, I've got a, which is the coefficient of the square root of x, and then b, coefficient of the square root of x. I can take that a and that b, and I can add them together because this is exactly the same. Okay, if it wasn't the same, x squared, or it could be anything. Okay, as long as it's not the same as the square root of x, then we cannot add it together. We cannot combine those coefficients. Okay, so it's kind of like an x, okay? But it even works for a number. So for example, if you look at this 5 root 2, 5 root 2 is a root 2, which means I have 5 root 2's, okay? I can only combine them with this one and this one. These are the only sort of like terms that I can add or subtract. They have to be exactly the same thing underneath the hood of the square root or the radical symbol. In other words, the radicand has to be exactly the same for us to collect like terms. So if we have 5 root 2's and we have negative 2 root 2's and negative 6 root 2's, it's really 5 minus 2 minus 6 is negative 3 root 2. And you can see here I collect my like terms together, like we did way back when as grade 9s. Okay, I put the root 3's together and the root 3's together. I've got a positive 4 root 3 and a positive 3 root 3, so that means that I have 7 root 3. So it's very simple. You take the types of roots, those what make the radicals like radicals, and then we add the coefficients. If they're not like, we don't add them. Okay? If we look at this example here, we've got a root 5, we've got another root 5, we've got another root 5, and then we got 2 root 3's. So the root 5 and the root 5 and the root 5 we can all add together. So negative 4 root 5, positive 4 root 5, and negative 9 root 5 is a negative 9 root 5. Negative 4 plus 4 minus 9 is negative 9. And it's root 5s, okay? Then we also have root 3s. We have a negative 3 root 3, and we have a negative 4 root 3, which leaves us with a negative 7 root 3. Okay, and that's the final result there. So again, it's kind of like collecting like terms with variables, except what is underneath the square root has to be exactly the same for us to be able to add and subtract things. So it's a very restrictive, very difficult thing to add materials or to add things together in mathematics. Okay, if I look here, I've got a root 6 and a root 6 and then a root 7 and a root 7. So again, I add the root 6's together. A 5 and a 4 give me 9 root 6. And then an 8 and a negative 1, okay, because there is one of them there. An 8 minus 1 gives me a positive 7 root 7. Okay? Now, there are some issues that happen along with collecting like terms because we tend to do addition and subtraction at the end of an operation. We do have to be careful to make sure that our radicals are factored or written in lowest terms. And writing radicals in lowest terms, I'll show you how to do that in a little bit. You need to do that first before you start collecting like terms because things may not look like they're the same type of square root, but they are in fact the same type of square root with a coefficient in front of them. And I'll show you how that works as well. Okay, so that's how we simplify radicals, addition and subtraction. Now we have the multiplication of radicals. We also can do division of radicals. It's just not too functional for where we are. Okay, and we don't do any rationalizing the denominator, so we keep it relatively simple. So this is the idea. We can multiply any radical by any radical. Okay? It's the same thing as x's and y's and coefficients and signs. They all like affects like. So in other words, when I go to multiply c times the square root of a, or c square root a, d square root b, I multiply the c times the d, the coefficient times the coefficient to get cd, and I multiply the root a times the root b. Now the root a and the root b stay in the root and stay underneath the square root. Okay, so you get a result. So in this case here, I'm going to take this number and multiply it by this. So I'm going to take the 2 and multiply it by the 4 to give me the 8. I'm going to take the root 3 and multiply it by root 5 to give me a root 15. Okay? And then I'm also going to go ahead and multiply this 2 root 3 times negative root 7. So 2 times negative 1 is negative 2. And root 3 times root 7 is root 21. Okay? And so as a result, well, these two roots are not the same, so I can't collect any like terms. So it's 8 root 15, excuse me, times 2 root 71. Now, if these weren't in lowest terms, we would have another step after this, but we haven't quite gotten to that whole point, so let's just keep it simple. For this one here, if I take a distributive property here, okay, this times this and this times this, okay, so again, I multiply c root a times d root b. It's in brackets, remember, so there's a distributive property happening here. So c root a times d root b, c times d, cd, a times b, ab, c times e, a times c, and we're left with these results. So here's an example of two binomials that I'm expanding. So I go 3 root 3 times 2 root 2. 3 times 2 is 6. Root 3 times root 2 is root 6. 3 root 3 times 4. 4 times 3 is 12. Root 3 times no root is root 3. Negative 1 times 2 root 2. Negative 1 times 2 is negative 2. No root times root 2 is just root 2. Negative 1 times positive 4, simply negative 4, nothing we're too crazy about. And you'll notice the roots are different, so we do not collect any like terms. Okay, so we'll do a couple of these ourselves, just to be sure we know what we're doing. I'm going to go this times this, this times this, and this times this. The same distributive property I would use if these were as a 2 and an x and a y and a z. Okay, so negative 2 times 2 is negative 4. The coefficients multiplied by the coefficients. And the roots by the roots. So root 3 times root 5 is root 15. Negative 2 times positive 3 is negative 6. Root 3 times root 3 is root 9. Negative 2 times negative 1 is going to be a positive 2. Root 3 times root 6 is root 18. Now, if you look at these carefully, you're going to find out there's a couple of interesting things that happen here. Negative 4 root 15. Well, 6 times root 9 is actually negative 6. The square root of 9 is 3. So I can actually go ahead and get rid of that square root in that particular instance here. There's actually something we can do with this 2 root 18, but I'm going to leave that for now until we understand another property of radicals. And then maybe we can come back. So I'm going to leave it at negative 4 root 15 minus 18 plus 2 root 18. And we'll leave it at that for now, and we'll get to that a little bit later on, okay? So we'll just focus on the multiplication here. Okay, here we've got quite the problem. We've got a binomial times a binomial, and then we've got a monomial out front, okay? So 2 root 3, I'm going to do the brackets first. So 2 root 3 times 5 root 6. I'm going to leave the 2 root 3 out front here. I'm going to use some square brackets, I think. 2 root 3 times 5 root 6 is 10. 5 times 2 is 10. Root 18. Plus, oops, maybe it's a minus. 2 root 3 times negative root 3 root 7. So 2 times negative 3 is negative 6. Root 3 times root 7 is root 21. Then I've got 2 root 5 times 5 root 6. That's going to be 2 times 5 is a positive 10. Root 5 times root 6 is root 30. And then 2 root 5 times negative 3 root 7. 2 times negative 3 is negative 6. Root 5 times root 7 is root 35. Then I continue to distribute these through. Okay. I can't collect any like terms because these aren't like, or at least I can't tell that they're like yet. Okay, there may be some that actually have some like terms in there and are reducible, but otherwise they're not. Okay, so then I go 2 root 3 times 10 root 18 is 20 root 54. Okay, the 2 times the 10 and the 3 times the 18. 3 times, yes. Okay, 2 root 3 times negative 6 root 21 is 2 times negative 6 is negative 12. Root 3 times root 21 is root 63. 2 root 3 times 10 root 30. 2 times 10 is 20. Root 3 times 30 is root 90. And 2 root 3 times negative 6 root 35. 2 times negative 6 is negative 12. Root 3 times root 35 is 105. Okay? And because the roots are not the same and we don't know what to do after that, we leave it as is. Okay? Now, what we have here is an operation where we can actually go back to these and look to see if we can actually, quote unquote, sort of reduce them or write them in lowest terms. Or really what we call them as, write them as a mixed radical or a factored radical. Okay, so we're going to learn about that process now, and then we'll work our way back and look at these again. Okay, so there's an interesting property of radicals that comes from the multiplication rule. Okay, usually I take the square root of a times the square root of b, and I multiply what's underneath the square roots to get the same number, and then I take those two numbers, I multiply them together, and I get that result. Okay, well, it can work the other way around. So if I take something under a square root, like the root of, I don't know, 50, I can actually turn that into maybe 5 times 10. Or I can turn it into 25 times 2. Or I guess I could turn it into 1 and 50. And those can actually be broken up into root 5 times root 10. Or root 25 times root 2. Or root 1 times root 50. So that's a neat property that you can get from radicals. And what's interesting for some of these is if I take the square root of 50, this is actually a perfect square. The square root of 25 is 5. So what this turns into is 5 times the root of 2. This also turns to square root of 1, which is 1. 1 times the root of 50. And this, unfortunately, doesn't really come out as anything because the square root of 5 and the square root of 10 are not perfect squares. So as a result, they don't reduce down or sort of decrease down to anything. But we use this property to be able to go back and forth. So I can take what's underneath the square root sign, and because it's multiplying, and turn it into 2 square roots multiplied apart. So they're together and apart, and I can go back and forth, okay, between those two forms. So let's do that. Okay. First, we have something called a mixed radical. A mixed radical would be like 5 root 2. That's a mixed radical. Okay, where there's a coefficient or a number part, whole number part, and then there's a square root part, which is an irrational number. So there's a rational and an irrational part. Whereas an entire radical is 50. Okay, where the square root of 50 doesn't have a number in the front other than 1, and so therefore it's really only just an irrational number, the square root of 50. Okay, and that's called an entire radical. So let's look at converting between these two. Excuse me. This means that we can interconvert between a mixed radical form, 5 root 7, to the product of two radicals. 5 is the square root of 25. to a final product called an entire radical, the square root of 175. So one operation is to go from mixed radical form to entire radical, and the other operation is to go from the entire radical to mixed radical. So let's look at factoring the radical. That's going from entire radical form to mixed radical form, entire to mixed. Okay? It's akin to reducing fractions, and it's a really useful thing so that we can see if we have any like radicals that we can collect like terms with for adding and subtracting. Okay, so if you're adding and subtracting radicals, this form must be used so you can see if the radicals are the same and simplify fully. So here is an entire radical, okay? Just a square root, nothing else. What I do is I say 80 is a bunch of numbers. It's 8 times 10, okay? It's 5 times 16. It's 4 times 20. It's a bunch of different ones. But what I do to factor it is I do it with the idea in mind that I will take a number out that will actually come outside of the square root sign and simplify to a whole number or an integer. And that would create the mixed radical form. So this is the entire form. And I want to go to mixed. Entire. Okay? So look for the largest perfect square that divides into the radicand evenly. So you look at 80 and say, what perfect squares divide into 80? Well, you try 1. That's not very helpful. You try 4. You know that 4 divides into 80 20 times. So you can break it up, into 4 and 20. But 4 and 20 aren't necessarily the largest radical. Let's see if something bigger can fit into it. So then you try 16. And most people forget that 16 times 5 is also 80. Okay? And as a result, 16 seems to be the biggest perfect square that goes into it. Then you keep on going. The next perfect square above that is 25, because it's 5 squared. 25 doesn't divide into 80 evenly. The next perfect square above that is 6 squared, which is 36, which doesn't divide into 80 evenly. And 49 definitely doesn't divide into 80 evenly. And nothing bigger than that. We don't even have to worry about it. It's not going to divide into evenly. So we found the largest perfect square that fits into it evenly, 16. And so we break it into the square root of 16 times 5. And then we break the square root of 16 into the square root and the square root of 5 up into 2 different roots. And then what we do is we take the square root of 16 and turn it into 4. And then the root 5 is kind of left over. So now we have a mixed radical that has an integer number and has an integer number of square roots of 5. Okay? So that's factoring the radical. So if I look at something like 128, I ask myself, what perfect square goes into 128 nice and evenly? Well, I can try the number 4. The number 4 goes into 28. Okay, it goes into it 32 times. So I could break this up into 4 times 32. The only problem is 4 the biggest perfect square? You may want to write your perfect squares somewhere nearby. So you've got 1. That one's useless. 4, 9, 16, 25, 36, 49, 64, 81, 100, and then after that you're kind of getting a little ridiculous, but who knows, okay? So then I look at it. If I do 4 times 32, let's just go and try that out first. If I break this into 4 times 32, then I break it into the square root of 4 times the square root of 32, and I break that into 2 times the square root of 32, I still have to ask myself, is that 32? Is there a perfect square that goes into 32? And if I can find another perfect square like 4 that goes into 32, I'd have to factor it again. I factor it again. That's when you don't have the biggest perfect square. Okay? So you want to pick the biggest perfect square that will divide it evenly. And it takes a little bit of playing around, a little bit of calculator work. And so what you do is you go, okay, 128 divided by 4. Yes, that works. So let's keep that on the back burner in case we want to use it. You try 128 divided by 9. No, doesn't work. 128 divided by 16. 16 goes into 128 8 times? 8? It does. It goes in 8 times. So maybe 16. That's a bit better. Keep going, though. 25 doesn't go into it. 36. Does 36 go into 128 evenly? 3 times 3 times 36 times 3 is 90. 4, I think it's going to be too big. Yeah. No, I don't think that's going to go into evenly. What about 49? Is 49 going? No, I don't think that's going to go. What about 60? 64 goes into 128 evenly. 81, 100, they're too big. In fact, 64 goes into it twice. So 128 can be written as 64 times 2. Now, the square root of 64 is a perfect square. So then I take my square root of 64, that becomes 8 times root 2. And now this is in entire, and this is in factor. Oops. Factored. And if we always have everything in factored form and in its simplest square root, then we know if we can, collect like terms and do some interesting things with that. So for this one, I kind of have an interesting thing going on here. First, I've got a 4 out front already. So it's already a mixed radical. But I want to take the square root and turn it into something smaller. And I can see right away that 25 goes into that nice and evenly. So I can break that into 25 times 5. 4. Then I go square root of 25, square root of 5. Then I go 4. Square root of 25 is 5 times the square root of 5. And of course, 4 times 5, I can write that as 20 root 5. And so that's in the lowest radical form. And I'm sure of that because if I look at that number, there's no perfect square that will go into that nice and evenly, other than, of course, 1, which doesn't make it any smaller. Okay? So now I'm going to expand these guys, and then afterwards, I'm going to write it in mixed radical form, in factored form, so I can see if I can collect like terms here. I probably won't be able to, but I still should be able to write my final answer in fully factored form. So 2 times 3 is 6. I'm doing that multiplication first. Root 5 times 15 is root 75. 2 root 5 times 2 root 20. 2 times 2 is negative 4. 5 times 20 is the square root of 100. Now, 6 root 75. Is there a perfect square that goes into 75? I think it's pretty obvious. It's 25 times 3 minus, 4. Square root of 100 is just 10. So that actually simplifies out, which is nice. So I'm kind of doing a couple of things at once. And of course, if this is a perfect square in and of itself, you might as well just square root it, figure out the final answer, right, as an integer value. Again, I still have the 6, the square root of 25 times the square root of 3. And I'll just make that 40. And then 6 times 5 times root 3 minus 40, which is 30 root 3 minus 40. And that's written in lowest terms, and I'm sure about those radicals that I can't collect like terms, mostly because one of them isn't even a radical at all. Okay, but if it was a radical like a root 5 or a root 2, I couldn't add it. Okay, but if it wasn't in simplest radical form, you couldn't tell. So make sure that whenever you do any work, you always end with factor your radical. Okay, always you end with that skill. Now sometimes it's useful to sort of go the other way around, to write a mixed radical, like this guy, as an entire radical. Okay, maybe to do some multiplication or whatever it may be. It sort of depends on what you're interested in. But there could be something interesting that goes along with this. So if you look at this, you say to yourself, okay, the number underneath the square root sign, I just leave as a square root. But I can always take any whole number and I can make it into a square root. All I have to do is take this number, 7, square it, and write it under a radical sign. And you can see right away that these two guys are exactly the same thing. Square root of 49 and 7 are exactly the same thing. But I don't want to have a coefficient. I want to have only a radical. Okay? So this allows me to have a square root times a square root and then multiply those values together. So I go 3 times 49 is the square root of 147. It's kind of the opposite of factoring the radical. Okay? Because you're putting in a factor that you could take out otherwise. So let's start with this one. Okay, the root 2 I'm going to leave as a root 2, but I'm going to write 5 as the square root of 25. Once I have it written as a square root of 25, it's 25 times 2, or square root of 50. And that's written as an entire radical, rather than a factored or a mixed radical. Okay? In this case, I even got the letter b in there. It's sort of interesting. Okay, so what do? Well, I've got the square root of b. Don't know what that is at all. Okay, can't even turn it into a number in the calculator. And this is the square root of 4. So then I say, okay, this is the square root of 4 times b, or the square root of 4b. Okay? And that means that the coefficient of any variable can be removed from the B and taken out in a mixed radical form. Or if I want to have it in an entire radical, there it is. Even something that's entirely composed of variables. If I wanted to write it as an entire radical, okay, all I would do is take the root B and the A and write that as the square root of A squared. And then I could take A squared times B, A squared times B. And then finally, the square root of A squared B. And then you'll see, of course, that that A squared is a perfect square that will come out in front when it's square rooted. But for now, we're doing the opposite operation. We want an entire radical. So to play around with those and to get used to using those, make sure your final answers are always factored radicals, unless they ask you to put them into entire radical form. And try these questions out. Okay, there's quite a few of them, but they won't take very long to do. And your homework assignment may also include section 3.1 to 3.3, but I've given you the review section and those key questions that are in the review section, so you're going to be doing a little bit of less work, or a lot less work, and covering 4 sections with me. So hopefully that works out well for you, and get to that work.